Section: Introduction. In this section, we explore diffusion models and their challenges in image synthesis, especially in achieving high-quality results on datasets like LAION. These models often require many sampling steps, leading to high latency in generating images, which hinders real-time interaction. To address this issue, we aim to develop a one-step text-to-image model that can enhance user experience and broaden its applications in 3D and video contexts. One approach to building a one-step model is to train a GAN from scratch. However, training text-to-image GANs on large and diverse datasets remains challenging due to the need to handle two complex tasks simultaneously: establishing correspondence between noises and natural images, and optimizing a generator model to map noises to images effectively. This unpaired learning, as seen in cycle GAN, is considered more challenging compared to paired learning, where conditional GANs can learn from ground truth correspondences. Our key idea is to tackle these tasks separately. We first establish correspondence between noises and images by simulating an ODE solver with a pre-trained diffusion model. Once we have these pairs, we then use a conditional GAN to map noises to images in a paired image-to-image translation framework. This disentangled approach allows us to leverage the strengths of both generative models, using diffusion models for finding high-quality correspondence and conditional GANs for fast mapping. By collecting noise-to-image pairs from a pre-trained diffusion model and treating the task as an image-to-image translation problem, we can utilize tools like perceptual losses and conditional GANs. Surprisingly, we find that training with a regression loss alone, without the GAN loss, can yield comparable results to more recent distillation methods but at a lower computational cost if the regression loss is carefully designed. In regression tasks, using perceptual losses like LPIPS preserves important details better than point-based losses like L2. However, perceptual losses are not directly compatible with latent diffusion models due to the need for costly decoding from latent to pixel space. To address this, we introduce latent LPIPs, enabling perceptual losses to work directly in latent space and significantly increasing batch size. We also introduce ensembled latent LPIPs for improved performance in latent space, demonstrating strong results with just a regression loss, comparable to guided progressive distillation. Additionally, we incorporate a discriminator in training, developing a multi-scale conditional diffusion discriminator named Diffusion 2 GAN. This framework distills stable diffusion 1.5 into a single-step conditional GAN model, outperforming other distillation methods on benchmarks like COCO 2014. Furthermore, we show the effectiveness of Diffusion 2 GAN in distilling larger models like SDXL, achieving superior FID and clip score compared to other one-step models. Our approach combines the strengths of diffusion models and GANs to enhance image synthesis speed and quality. Section Summary. In this section, we introduce the challenge of high latency in existing diffusion-based image generation models due to the need for multiple sampling steps. To address this, we propose a novel approach called Diffusion 2 GAN, which distills a pre-trained diffusion model into a single-step conditional GAN model. By leveraging tools like E-latent LPIPs and a multi-scale diffusion discriminator, our Diffusion 2 GAN outperforms other distillation methods like UFO-Gen and DMD, showcasing superior performance on the COCO 2014 benchmark and in distilling larger models like SDXL. Section: Method. In this section, we aim to simplify a pre-trained text-to-image diffusion model into a one-step generator. Our objective is to train a one-step generator network, denoted as G, to map input noise, Z, and text VB, C, to the output of the diffusion model, X. We assume that both the student and teacher models share the same architecture, allowing us to initialize the student model G with the teacher model's weights. We focus on latent diffusion models where X and Z are in a specific dimensional space. Later, we extend our method to the SDXL model. We will explain the design and training principles of our framework in detail. We start by discussing distillation as a paired image-to-image translation problem. Then, we introduce our ensembled latent LPIPS regression loss, E-latent LPIPs, which enhances training efficiency and distillation performance for latent diffusion models. Additionally, we introduce an improved discriminator design that utilizes a pre-trained diffusion model. It is important to note that our approach is not limited to a specific type of latent space diffusion models and can be applied to pixel space models as well. We explore a method called paired noise to image translation for one-step generation. This method simplifies the multi-step denoising process of a pre-trained diffusion model into a single step by minimizing a distillation objective. The objective involves using Gaussian noise samples, a text prompt, a U-net generator, and the output of the diffusion model. We use pre-computed pairs of noise and corresponding solutions to an ordinary differential equation, ODE, to reduce computational costs during training. By incorporating a perceptual loss and scaling up the ODE pair dataset, we significantly enhance the quality of distillation, as demonstrated in our experiments on the CIFAR-10 dataset. Furthermore, we introduce ensembled latent LPIPs for latent space distillation. We modify the original LPIPS to operate directly in the latent space without the need to decode into pixels. By training a VGG network on ImageNet in the latent space of stable diffusion and calibrating intermediate features, we develop a function that computes perceptual distance in the latent space. This new loss function, named E-latent LPIPS, improves convergence and reduces computation time and memory consumption compared to traditional LPIPS. Our experiments show that learning the ODE mapping with E-latent LPIPS leads to better convergence and lower FID compared to other metrics. The use of differentiable augmentations further enhances the reconstruction process. For more details on our experiments and augmentations, please refer to the appendix. Section Summary. In this section, we aim to distill a pre-trained text-to-image diffusion model into a one-step generator by learning a mapping X equals G, Z, V, B, C. We assume the student and teacher share the same architecture, allowing us to initialize the student model G using the teacher model's weights. Our method extends beyond latent space diffusion models to pixel space models, improving distillation performance through techniques like ensembled latent LPIPS regression loss and an improved discriminator design. Section. Conditional diffusion discriminator. In this section, we explained how we approached diffusion distillation by framing it as a noise-to-latent translation task. We were inspired by the success of conditional GANs for image translation tasks and decided to use a conditional discriminator. This discriminator considers both the text description and the Gaussian noise given to the generator. By incorporating this conditioning and utilizing pre-trained diffusion weights, our new discriminator aims to optimize the generator and discriminator through a minimax objective. For the generator, we focused on minimizing a specific GAN loss to improve its performance. We also discussed the initialization process from a pre-trained diffusion model, which proved to be effective for diffusion distillation. By initializing the discriminator weights with a pre-trained model and fine-tuning it in the latent space, we achieved better results compared to using a GigaGAN discriminator. To enhance the discriminator architecture, we made modifications to support conditioning on the input noise map. This was done by adding the input noise processed through a convolution layer. Additionally, we introduced single-sample R1 regularization to improve training stability and convergence. This regularization method helped address training variance and gradient issues in the discriminator. Furthermore, we proposed a multi-scale U-net discriminator design to ensure that all layers contribute to the final prediction, leading to improved structural consistency and better results. We also implemented mix and match augmentation during discriminator training to encourage better text alignment and noise conditioning. In our experiments, we conducted systematic studies to evaluate the effectiveness of our algorithmic designs and compared our method with other generators using various benchmarks. We trained our model on different datasets with classifier-free guidance and simulated the ODE using DDIM sampler. Our evaluation focused on image quality and text-to-image alignment using FID and clip score metrics on COCO 2014 and COCO 2017 datasets. Overall, our approach, named Diffusion 2 GAN, showed promising results in improving image realism and text-to-image alignment, demonstrating the effectiveness of our proposed techniques in diffusion distillation. Section Summary. In this section, we introduce a conditional diffusion discriminator that leverages pre-trained diffusion weights and incorporates text descriptions and Gaussian noise for improved diffusion distillation. We optimize a minimax objective for the generator and discriminator, utilizing a non-saturating GAN loss for the generator. By initializing the discriminator with a pre-trained diffusion model, applying single-sample R1 regularization, and introducing a multi-scale in and out U-net discriminator design, we enhance stability and convergence, leading to superior FID scores. Additionally, mix and match augmentation is employed to encourage better text alignment and noise conditioning during discriminator training. Section: Effectiveness of each component. In this section, we conducted an ablation study to analyze the effectiveness of each component in ode distillation training. We tested different distance metrics such as L1, pseudo-Huber, LPIPS, latent LPIPS, and RE latent LPIPS. Our findings showed that using MSE for ode distillation led to worse results on large-scale text-to-image datasets. However, incorporating the pseudo-Huber metric improved the FID significantly, though not adequately. When we included perceptual losses like pixel space LPIPS and latent space E latent LPIPS, the ode distillation yielded promising results with FID around 20 to 25, even with a small batch size. This indicates that the noise-to-image translation task has potential, especially when a conditional discriminator is introduced to enhance image quality. Furthermore, we examined each component of the Diffusion 2 GANs discriminator through an ablation study. All generators were initialized with the best-performing ode distilled generators pre-trained weights. By comparing our diffusion-based discriminator to the state-of-the-art GAN discriminator, we observed that each component of Diffusion 2 GAN played a vital role in improving FID and clip score. Diffusion 2 GAN outperformed ode distillation with the GAN discriminator and narrowed the performance gap with the stable Diffusion 1.5 model. We also compared Diffusion 2 GAN with other cutting-edge diffusion distillation models on COCO 2014 and COCO 2017 benchmarks. While models like INSTAFLOW 0.9b achieved certain FID scores, Diffusion 2 GAN proved to be more effective in handling the ode distillation problem with lower FID scores. Even when compared to models like UFOGen, MDUFOGen, DMD, and ADDM, which use additional diffusion models for training, Diffusion 2 GAN showed superior performance by closely following the teacher diffusion model's trajectory to maintain high visual quality and mitigate diversity collapse issues. Moreover, we distilled the SDXL Base 1.0 model into Diffusion 2 GAN and evaluated its performance on COCO 2017. We introduced a new metric called DreamDiv to measure image diversity, which considers the average pairwise perceptual distance between generated images. Our results showed that SDXL Diffusion 2 GAN achieved comparable FID and clip score with SDXL Base 1.0 while exhibiting higher DreamDiv compared to SDXL Turbo. Additionally, we introduced DREAMSIM5K to assess the learning capability of the diffusion teacher's ode trajectory, showing that SDXL Diffusion 2 GAN performed better in learning the noise image mapping compared to other models like SDXL Turbo and SDXL Lightning. Section Summary. In this section, we conduct an ablation study on different distance metrics for ode distillation training, including MSE, pseudo-Huber, LPIPS, latent LPIPS, and E latent LPIPS. We find that using perceptual losses like LPIPS and E latent LPIPS significantly improves FID scores in ode distillation tasks, hinting at the potential of noise-to-image translation. Additionally, our Diffusion 2 GAN model outperforms ode distillation with the GAN discriminator and narrows the performance gap with stable Diffusion 1.5, showcasing its efficiency in handling the ode distillation problem. Section: Visual Analysis. In this section, we visually compare our model with stable Diffusion 1.5, LCM LoRa, and InstaFlow. We train our Diffusion 2 GAN using the SDCFG8 dataset and compare it against stable Diffusion 1.5 using the same guidance scale of 8. Our model produces images with enhanced realism compared to the other distillation baselines while maintaining the overall layout of the target images generated by stable diffusion. We couldn't compare Diffusion 2 GAN with more advanced distillation models due to the unavailability of pre-trained weights. Therefore, we compare these models quantitatively in tables. We also compare Diffusion 2 GAN, distilled on SDXL Base 1.0, with SDXL Turbo and SDXL Lightning. Diffusion 2 GAN is the only model capable of following the ODE trajectory of the teacher diffusion model. It generates more diverse images than SDXL Turbo and exhibits more plausible structural features than SDXL Lightning. Regarding training speed, Diffusion 2 GAN converges more efficiently than existing distillation methods. On the CIFAR10 dataset, training with the LPIPS loss on 500K teacher outputs surpasses the FID of consistency distillation at a fraction of the total compute budget. Our full version Diffusion 2 GAN achieves superior FID compared to InstaFlow while using considerably fewer GPU days for text-to-image synthesis. We have introduced a new framework, Diffusion 2 GAN, for distilling a pre-trained multi-step diffusion model into a one-step generator trained with conditional GAN and perceptual losses. Our study demonstrates that separating generative modeling into two tasks allows us to use different generative models to improve performance runtime trade-off. Our model is beneficial for interactive image generation and offers potential for efficient video and 3D applications. However, our method has limitations. It simulates a fixed classifier-free guidance scale and does not support varying CFG values at inference time. Exploring guided distillation methods could be a promising direction. Additionally, the performance limit of our model is bound by the quality of the original teacher's output. Leveraging real text and image pairs could help improve the student model. Although Diffusion 2 GAN alleviates the diversity drop, we have observed that it still occurs as we scale up the student and teacher models. Further investigation of this issue is left for future work.